Hey everyone! Today I found a very interesting physics problem, and I thought I'd share my solution. First I'll talk about the problem, and then we'll run down how I tackled it. In this situation, we have a truck of mass m holding a bag of rice with little mass m. This system is being acted upon by a horizontal force F, which is pushing it to the right. Simultaneously, there's a small hole in the truck, which is letting the rice out at a rate of dm over dt, which we set equal to y. We'll see why in a little bit. The goal of the problem is to find the speed of the truck after 1/2 of this little mass m is dispensed. The key to tackling this problem is to use the ideal rocket equation, which I'll write out now. Where u refers to the speed of the expelled mass. In order to relate this equation to the problem, we're going to have to make a couple substitutions. The first asking this question of what really is this variable m right here. Naturally, this car isn't going to have a constant mass because it's emitting some of the mass. So what we can do is I'm going to define real quick a new variable that I'm going to call mt, or how about ms, which refers to the mass of the system. That's going to equal, initially, m plus this little m, right? We're just taking the bag of rice, we're adding it to the mass of the truck, and there we go. It's the mass of the whole system. Now, ms, as a function of time, is going to be this initial ms minus the rate that we're expelling the mass times however much time has gone by, right? This should intuitively make sense. We're simply taking our original mass and subtracting away the rate that we're expelling the mass times the time. I'll go ahead and make this substitution. The next thing to think about is our second term, our negative u dm over dt. And what we're going to see here is that u is actually going to equal 0, because in terms of our motion, which is to the right, there is no horizontal velocity that this expelled rice is going to have. Therefore, u equals 0. Meaning that this entire term drops out. So what we have here, and I'll go ahead and write F external as just F, right? We just have this one horizontal force F on the car. Here is our little equation of motion. Now, what we need is to find a function for the velocity. So, I'm going to isolate dv and then we'll integrate. And there we go. Let me make that fraction a little bit nicer. Okay. So, we're going to integrate these, and we have to think about our boundaries for a second. So, we'll begin at 0, and we're going to go to time T final, right? And T final refers to whatever the time when a half of that mass is dispensed. Naturally, we're going to have to make a substitution at some point to really define what that time is. But for now, T final is good enough. So here then refers to E of T final. Now, in order to do this, we're going to have to think about U substitution to solve this integral on the left. So that's what I'll go ahead and tackle first. Let's go ahead and write out the integral. This force F, I'm going to go ahead and take and put outside the integral. So this is really 1. Next I'm going to say that U equals m naught minus gamma t du equals negative gamma dt. Therefore, dt equals negative du over gamma. I'll go ahead and make these substitutions real quick. So we have negative f over gamma, and I keep calling this gamma or y. I keep like interchanging it because those symbols look similar. Sorry about that. They're the same thing. They're the rate of the expelled mass. Anyways, so we go from the integral from 0 to final of 1 over u du. Okay. This is going to equal the natural log of u, which I'm going to resubstitute in my m naught minus gamma t. So this is negative f times the natural log of m naught minus gamma t over gamma. I swear the hardest thing with these is making a straight like fraction bar line. Like I practically should just be using the line tool for this and it would look nicer. Anyways. And we're going from 0 to t final. Now, we need to tackle this question of what is t final? And to do that, I'm going to set up a function for my little mass as a function of time, which I'm going to call and as a function of time equals. So we have our initial total mass, which is m, little m, minus, again, gamma t. In our situation, we said that we're looking at when m of t equals 1/2 m, 1/2 of the initial mass. So I'll make that substitution. And I can solve for m, which is going to equal m naught, the initial mass, or whoops, this should be t. T equals m over 2 gamma. So I'll go ahead and replace this boundary with m over 2 gamma. Okie dokie. So, all we have to do is plug things in. So this is negative f, natural log, f naught, minus gamma times m over 2 gamma, which those will cancel, over gamma, minus a negative f over gamma times natural log of just m naught, because t here is 0. Now, we can ultimately recombine these, so I'll write this out in 2 steps, just so that we're clear. We can rewrite this as f over gamma times the natural log of m naught minus the natural log of m naught minus m over 2. Which we can then write, I'm going to shrink some of this work up a little bit so I have space. Just based on using rules with natural logs. Now we can write this as f over gamma times the natural log of m naught over m naught minus m over 2. And this is what our final velocity is going to be equal to. And with that, thanks for watching.